Swayam Prabha. Digital India. Educated India.
Welcome to the DTH sponsored course on micromachining. Today I am going to discuss about wire electrochemical micromachining, which is abbreviated as wire ECMM. Acknowledgement: Swayam Sharma et al., who have published a chapter on wire electrochemical micromachining in the book on advanced machining science, published by CRC Press, USA. PhD thesis of Dr. Swayam Sharma from IIT Kanpur, advanced machining science book, CRC Press, USA, and help extended by Dr. Swayam Sharma and Dr. Mahavir Singh from IIT Kanpur. Organization: Introduction to Wire Electrochemical Micromachining. Elements of wire ECMM system. It should not be EDMM. It should be ECMM. Then process parameters and characteristics, applications and conclusions. Introduction to wire electrochemical micromachining. It is difficult to machine. There are various materials which are difficult to machine. Advanced engineering materials such as titanium, tungsten, nickel, metallic glasses, etc. by conventional machining methods like turning, milling, drilling, etc. because tool hardness issue is there. Tool hardness should always be much greater than the workpiece hardness. While these materials, some of these materials in their alloy have hardness which is more than the tool hardness. Hence, it becomes difficult to machine them by conventional methods. Tool geometry and kinematics of machining have to be modified according to the application of the system or application of the machining method. Solution is non-contact advanced machining processes like laser beam micromachining, ultrasonic micromachining, electrochemical micromachining, electric discharge micromachining, etc. ECM, the process in which no heat is generated and no mechanical forces are acting on the workpiece. It does not alter surface morphology of the machine component as compared to the original morphology of the surface, except very minutely, if at all, anywhere. Different variants of ECM: shape tube electrochemical drilling, that is also abbreviated as STED, electrochemical turning, ECTRG, jet electrochemical machining, wire electrochemical micromachining or wire electrochemical machining. Only difference between wire ECM and wire ECMM is the size of the feature that you are creating by this process. Achieved significant level of maturity. So, wire ECMM has achieved maturity and it is being used on the shop floor in some of the advanced industries. Machining capabilities of wire ECMM process like accuracy, efficiency, surface quality are unaffected by the mechanical properties of the workpiece, namely hardness, toughness, etc. Mechanism of material removal is same as the mechanism of electrochemical micromachining and electrochemical machining. So some of the things may be repetition as compared to ECM, so you have to bear it. Electrodes are placed in the electrolyte and electric current is passed through them. Ions are transferred between the electrodes, means anode and cathode, and electrolytes resulting in the removal of material from the anode. Here please note it carefully. Material is removed from the anode only, that is the workpiece, not from the cathode, that is the tool, and here tool is wire. A quantitative relationship between the mass of material removed m and the electric current passed through the circuit is given by Faraday's law of electrolysis. As I mentioned earlier, it works on the same principle as ECM, and ECM and ECMM work on the Faraday's laws of electrolysis. Now here you can see the mass of the material removed is given by Q over F multiplied by A over Z, where Q is total electric charge passed in the circuit, P is the F is the Faraday's constant and its value is 96,500 coulomb per mole. A is the atomic mass of the anode material and Z is valence number of ions of anode material during electrolysis. And here when I am saying Z alone, it is for pure metals. If it is the alloy, then different elements will have different Z and you have to evaluate the value of Z for that particular alloy separately, and that has been discussed in the book. If you want, you can see on advanced machining processes. Positive metal ions leave the workpiece and electrons leave the tool to reach their respective opposite ends. The anodic reaction leads to the formation of metal anions compounds. Now these anion compounds are heavier than other ions and losing H plus, that is hydrogen plus ions, which reduces H plus ion reduces the electrolyte conductivity, and we are using electrolyte which is electrically conductive. As machining progresses, the conductivity decreases due to the formation of electrically non-conducting electrolysis products, because sludge is formed due to the ECM as well as in wire ECMM, and this sludge is mostly electrically non-conductive, hence it reduces the conductivity of the electrolyte, and pH increases due to an increase in the hydrogen ions concentration. We have already seen the hydrogen ions are removed and they are there, so they reduce the or they increase the pH. Metal hydroxide and metal chloride would form and get precipitated as sludge when aqueous sodium chloride, that is NaCl, is used as an electrolyte for machining of steel. So I am specifically mentioning steel. Now you have to use different electrolytes for different materials. You can see here where ECMM setup, different motion controller is here, power supply is here, PC for controlling the system is here, and you can see here oscilloscope to see the pulse shape, electric pulse or electric power pulse shape you can monitor from here. And then you have the enlarged view of this machining area. Here is the wire that is shown over here, workpiece is there, and then you have electrolyte recirculation system, because electrolyte, this is the electrolyte tank, so electrolyte is coming out, then electrolyte pump is there, then filtration takes place, and before recirculation, filtration has to be done very carefully. Now this is the enlarged view of this part. This is the wire which is really cutting. As you can see, this is the kerf produced by the wire by electrolysis or by electrochemical machining action over here, and path traced by the tool in the workpiece is like this. You can clearly see it here. So it is a schematic diagram showing wire ECMM setup. In wire ECMM, wire, that is the tool, is connected to the negative terminal, and it is known as cathode, of a constant or a pulsating DC power source. That DC power source is here, and this is the wire. This wire traces the defined trajectory in a workpiece which is connected to the positive terminal. As you can see over here, this is traveling in this defined trajectory and cutting it and giving a particular shape and size to the workpiece. Electrically conducting fluid, that is known as electrolyte, is supplied between the two electrodes, that is anode and cathode, and a feature of the desired shape is machined. This is the feature of the desired shape is being machined. If the tool is made of material which is chemically inert, no reaction with the electrolyte, no material gets dissolved from it, that is from the tool, and we really do not want any removal of the material from the tool, that is the wire. Otherwise it will affect the accuracy, that is the tolerances of the machine surface. Consequently, the same wire can be used repeatedly for machining, since there is no removal of the material from the wire. Hence you can recirculate or reuse the same wire for many components. Experimental setup, I have shown to you something schematic diagram. This is the experimental setup that was designed and developed at IIT Kanpur. You can see micro positioning controller over here, Mach3 GUI, used electrolyte exit tube. This is the tube which is taking the used electrolyte to the tank where it will be filtered before recirculation. And here is the motorized linear stage XY for XYZ, power supply unit is there, and electrolyte tube is again there. And this is the schematic diagram. This is the wire, this is the electrolyte being supplied, and this is the workpiece being cut. This is the another view, electrolyte and wire, same thing. Wire electrochemical turning. Now this particular process can be used for different kind of the operations. You can perform wire electrochemical cutting, wire electrochemical turning, even wire electrochemical drilling kind of the things you can do, different depending upon how you have designed and fabricated the setup. So here you can see this process is being used for turning operation. Close up image of the machining setup. This is the workpiece to be turned. This is the rotating chuck which is holding this particular workpiece, and wire is there, not very clearly visible. So you can use it for the turning operation. And we all know turning means reducing the diameter of this particular workpiece. But close up image of the machining setup that is shown over here, and here is the tool workpiece motion in wire electrochemical turning operation, and here you are doing threading kind of the operation. You can clearly see the workpiece is rotating. This is power, it is connected to the power supply, that is it becomes anode, and this wire is connected to the negative power supply, that is it becomes cathode. And here is the electrolyte that you can see over here, delivery system is there, and this is the kind of the cavity or the feature you are going to get on the machine surface after turning operation. You can see another view, schematic view for this, another direction of tool radial motion in this particular direction with reference to this workpiece, and direction of tool axial feed motion in this direction is the axial feed motion, and this is the wire workpiece, and you can see that 0 degree, 90 degree, 180 degree, 270 degree. So a close-up image of actual machining setup developed at IIT Kanpur, that is given over here. B, tool workpiece motion in wire electrochemical turning operation, that is shown over here, and a schematic showing the characterization of a typical groove profiling. You can make the groove over here with the help of this wire on this particular workpiece. Elements of wire ECMM system. Setup development for wire ECMM for texturing operation at IIT Kanpur. And this texturing operation is very important, because by making the texture, micro nano textures on the workpiece, you can change its characteristics, its property, its friction characteristics, and so on. So this is the setup which was developed at IIT K by Professor Divyans Patel of IIT Bhubaneswar, and you can see over here same thing, more or less the same thing which you have seen over in the earlier slide. This is the machining chamber shown over here, power circuit details are there, oscilloscope, function generator, power supply are here, and you can clearly see triangular shaped pulses, power pulses are being supplied in this particular case. Same thing, I am not going to repeat it. Broad classification of wire ECMM, wire electrochemical micromachining setup. Please see it carefully. Now this can be classified into different ways. First one, based on number of wires that you are using. If you see here, there is the single wire electrochemical micromachining. This is the workpiece and this is the wire, and it is cutting over here. But to enhance the performance or the material removal rate and capabilities, you can use multiple wires working at the same time. So you can see here there are 4 wires which are simultaneously cutting the same workpiece and enhancing the performance of the process. It can be classified based on electrolyte supply configuration. You can have inclined jet. This is the jet which is inclined as compared to the axis of the wire. Axial flow, and this is the axial flow jet, and this is the axis of the wire, and this is the axis of the nozzle which is supplying the electrolyte. And third is the submerged one. Here this is the electrolyte tank, this is the wire, this is the workpiece, and this electrolyte is filled up. So workpiece and wire both are submerged over there. You can also classify based on workpiece geometry. Workpiece can be flat, as you can see over here, or workpiece can be cylindrical like this over here, which is being turned. Based on tool workpiece dynamics, vibration assisted wire electrochemical micromachining. But this is the workpiece, this is the wire which is giving the vibrations, rotating tool. This is the tool which is rotating and working as the wire or the tool for removing the material from the workpiece, and this is the traveling tool. So this wire is continuously traveling in this particular direction and performing its operation in wire electrochemical micromachining. So it is image showing a broad classification of wire ECMM process. Electrolyte supply configuration in wire ECMM. We have seen 3 ways to supply electrolyte: inclined jet, axial jet, and submerged. We have already seen in the earlier slide. Inclined jet, the momentum of the high pressure jet may cause the wire to swing radially, leading to frequent short circuit. This is the disadvantage of this type of the system, and if short circuiting takes place, it will lead to the tool breakage and poor machining accuracy. The tool holder assembly is simple and wire can be changed rapidly. In the event of breakage, wire can be stationary or monodirectional traveling. It may be traveling there, which we have seen in the figure also. Hence, keep the wire under tension. This is very important. You should always keep the wire under appropriate tension so that you can avoid this short circuiting. which will lead to the wire breakage. Detailed investigation is due on the influence of angle of inclination of electrolyte jet on the process performance in wire ECMM. That means you have to find out the optimum value of the angle of the inclination of the jet, so that it gives you the best performance and minimal wire breakage. Axial jet, that also we have seen in the earlier slide. Electrolyte is flushed in the direction along the axis of the tool. Here the tool is wire, along the axis of the wire. Radial swing of the wire due to the momentum of high speed electrolyte jet. Speed of the electrolyte jet is quite high, so it will have certain momentum, and jet can be avoided and thick workpieces can be machined if you are having the axial jet. And then it requires properly designed tool holding system, which includes a nozzle with an electrolyte inlet passage. A stationary wire is used and vibrations may be given to the workpiece. Please note it carefully that it is not necessary that you use the travelling wire in wire electrochemical micromachining or wire electrochemical machining, because as we have seen earlier, we will see it later also, electrolyte is not consumed and wire is having no removal of material from the wire. Hence the wire strength remains the same and you can keep it using repeatedly. However, there are certain constraints which you will know later on. Submerged, tool and workpiece are submerged in the stagnant electrolyte bath. Here tool and workpiece are stationary, both are stationary. Due to the stagnant state of electrolyte, removal of electrolysis products and gas bubbles from the narrow inter-electrode gas is not spontaneous. In the other two systems, removal of the sludge or electrolysis products and the gas bubbles is spontaneous and they flow along the flow of the electrolyte in axial jet as well as inclined jet. But in submerged case, it is not so. So you may have to agitate the electrolyte for this purpose, so that the conductivity of the electrolyte becomes constant in the tank and this one sludge gets distributed in the whole electrolyte, and also the gas bubbles, they go out. So tool workpiece vibration is used to accelerate flushing of electrolysis products from the gap. So this is an alternative way. So you can adopt one of the or both of them depending upon the requirement and availability. Electrolytes used in wire ECMM, we have seen little bit of it. Now it depends upon which material you are going to machine. Is it pure or alloy, and what is the material? Based on that you have to choose the right kind of the electrolyte for that purpose. Material you can have like cobalt based superalloy, you can is the H2SO4, HF, HCl, C2, H8O7 and so on. You can use in some cases NaOH, KOH, basic electrolyte, these are the acidic electrolyte. Then you can use the neutral electrolytes also, that is the salt, etc. Material machines are tungsten, tungsten carbide, inconel, carbon steel, stainless steel, copper. You can use for these materials NaCl, KCl, NaNO3. They are known as neutral electrolytes. Titanium, aluminum, vanadium are the constituents, mild steel, aluminum. So you can use different kind of the electrolytes. Like materials machined are like this. Mixture of neutral electrolytes, this is very important to note, because in many alloys you may be required to use mixture of electrolytes rather than single electrolyte. But you should be careful when you are using mixture of electrolytes. Those constituent electrolytes should not react with them, with them itself. Different types of electrolytes are used in wire ECMM and material machine using by them. Note, a mixture of phosphoric acid in ethanol and water is used for the machining of cobalt based alloy. So, mixture is used for machining of the alloys. Eco-friendly anhydrous citric acid is used for the machining of stainless steel 304. The complex ions accelerate the dissolution and a high material removal rate is achieved. Types of electrolytes used in wire ECMM again continues. 3 types of electrolytes used in wire ECMM we have already seen in the earlier slide: neutral, basic, acidic. Neutral electrolytes NaCl, and some more details are given over here in this slide as in addition to what we have already seen in the earlier slide. A non-passivating electrolyte, high processing efficiency, better stabilized and low cost, but low machining precision. This is very important, but it is a disadvantage, and greater corrosion of equipment or higher probability of corrosion of the surrounding equipment and the equipment where it is being performed also. NaNO3, a passivating electrolyte, it offers high precision and low corrosion of equipment, but it gives low processing efficiency. NaCl gives high processing efficiency, but some disadvantages. It gives low processing efficiency, but some advantages. Then you have KCl, again neutral electrolyte, neutral salt, non-passivating, uniform and stable machining without getting affected by the passive oxide film, passive oxide film. Basic electrolytes, NaOH, sodium hydroxide, generally avoided because high hydroxide ion concentration increases the precipitation of metal hydroxides. We get metal hydroxide as the reaction product, just like ferrous hydroxide or ferric hydroxide. Now, in case of KOH, basic electrolytes, KOH, a basic electrolyte used for machining pure tungsten, passivating tungsten oxide film breaks readily in the presence of ions. This may clog the inter-electrode gap IEG and sometimes may even lead to the termination of machining operation. Acidic electrolytes, please note it carefully, this sentence holds true for the NaOH, not for KOH. Advantage, acidic electrolytes, advantage, reaction products remain dissolved in the solution, which is not the case in case of neutral electrolytes and basic electrolytes. Hydroxide ions produced at the cathode are neutralized by the high concentration of hydrogen ions in the solution, certain materials. So, we continue with the types of the electrolyte used in wire ECMM. We continue with the HCl. In the presence of aqueous HCl as the electrolyte, pitting corrosion of metallic glass usually occurs. Passive film breaks down due to the adsorption of chlorine ions. HCl is also used for the machining of cobalt based superalloys. Major problem in machining using HCl is blackening of the wire due to the precipitation of metallic iron on wire. High frequency vibration of tool and or workpiece is recommended for efficiently flushing out of reaction product. Now, HF, hydrofluoric acid, used for the machining of silicon. Passive film of silicon oxide easily gets dissolved using this strong acid. Anhydrous citric acid, it is used as an eco-friendly solution for the machining of stainless steel. Mixture of electrolytes are used, as I have mentioned in the earlier slide also. Electrolyte prepared by the mixture of 2 or more than 2 neutral salts or mixture of neutral and basic salts depending upon your requirement. In equal weight percent is used for the machining of titanium alloy. What weight percent is to be used will depend upon the percentage of different elements in the alloy also. However, not much research has been carried out in this direction, hence I do not want to say anything with a strong opinion. Not much discussion is available on the microstructure and roughness of the machined surface using mixture of electrolytes, because it is going to definitely affect the microstructure of the machined surface as well as roughness of the machined surface. It is the area where lot of research can be conducted. This area needs further research to support the claim of the experimental findings that the electrolyte mixture usually gives better results in case of an alloy dissolution. Tool materials in wire ECMM. Tool material for wire ECMM should possess good chemical stability, good etch ability and wettability, low electrical resistivity and good tensile strength. These are the basic requirements of the material to be used for making the wire. Copper has low electrical resistivity. Its poor chemical stability limits its use as a tool material. Wire of tungsten, stainless steel, molybdenum, copper, carbon nanotubes, that is CNT, platinum, brass and tungsten carbide are used till date. Tool made of chemically stable material does not form any precipitate during machining, which will restrict the mobility of ionic species in the interelectrode wire. So, what I mean to say that you have to see from all aspects the properties of the material to be used for wire, making wire or the tool. Carbon nanotubes offer high tensile strength and wettability, but very limited work has been reported on its use as a tool material because of certain constraints are there. Continuous tool material in wire ECMM. Carbon nanotubes offer high strength, wettability, but very limited work has been reported on its use as a tool material. This is possibly due to its poor electrical conductivity. Although CNT has 5 times electrical conductivity as compared to copper at nanoscale, but when thousands of CNTs, carbon nanotubes, are woven together to make a wire, its conductivity decreases drastically. A wire made of CNT has to be electroplated with conducting material such as aluminum to improve its conductivity. That is why CNTs have very limited applications as of now in wire electrochemical micromachining. The diameter of tool used in wire ECMM varies from 2 mm tungsten, not commercially available, to 2.8 mm brass, and this relates to the wire electrochemical machining, because this is for macro machining, and if it is for micro machining, then the diameter of the wire has to be smaller than 1 millimeter. It has to be few tenths of micrometer or a couple of 100 micrometers. To prevent the wire from swinging radially due to the force exerted by the gas bubbles, because gas bubbles are evolved during electrochemical micromachining. So, exerted by the gas bubbles and momentum of electrolyte jet, it is kept in a tensed position. I have already mentioned that wire should be properly tensed, otherwise it will have lot of repercussions, especially it may lead to the short circuiting and breakdown of the wire itself. This tensile force usually varies from 2 Newton to 50 Newton. Tool material must have sufficient tensile strength to withstand this tensile force even when the wire diameter is very small. Platinum is a chemically stable metal and its wires of diameter as small as 0.6 millimeter are commercially available, but their use in wire ECMM is limited due to their poor tensile strength. Please note it carefully. This, when we are talking of micro machining, then this diameter has to be much smaller than 1 millimeter, and it may be around 10 to 20 micrometer. When we are using such a thick wire, we don't call it as electrochemical micro machining, rather we call it as wire electrochemical macro machining. Tungsten is the most widely used tool material due to its high strength, high tensile strength and good chemical stability. Tool design in wire ECMM further continues. Apart from a tool with a smooth surface, textured tools have also been tested in wire ECMM for enhancing mass transport. You create a certain type of the textures, like pits are created deliberately or pillars are created on the wire, and that may enhance the performance of the process, because you are not throwing away the wire after using once. So once you have created those textures, this wire can be used for long period. You can see here rough wire surface, dimple like microstructures are created, that is the textured kind of the wire which is used for wire electrochemical micromachining. And you can see the dimensions, this is the 50 micrometer. So please note it carefully. If by mistake I have written at some places mm, in fact it should have been micrometer, not millimeter. And you can see very useful and interesting picture over here, twisted CNT wire. This is carbon nanotube, not F, this should be T. This is the CNT wire. So it has been twisted, and I have already told you that after twisting it has to be covered with certain layer like aluminum etc. to enhance its electrical conductivity. And you can see here ribbed wire like this here, these are the ribs over here. So different kinds of the wires have been used to enhance the performance of wire electrochemical micromachining. Improvements in tool designs and textures with time. You can see over here introduction of tube with micro hole arrays, introduction of twisted carbon nanotube fiber that is shown over here, introduction of cutting edge wire, ribbed wire is over here, introduction of rotary helical electrode, you can rotate the tool, introduction of wire ring and smooth and straight cylindrical wire. So in different years, different type of the wires for wire electrochemical micromachining and wire electrochemical machining have been proposed by different researchers across the globe. So you have to choose it appropriately according to your requirement of the machine component. Tool design in wire ECMM continues. A smooth cylindrical wire is not effective in pushing the electrolysis products out of the inter-electrode gap when axial vibrations are imparted to the tool or to the workpiece. This is because of its limited wettability. This is very important point, that textured wires are used because it helps in removal of the sludge etc. from the gap. Imparting some degree of roughness on the surface of a wire makes it more hydrophobic in nature, hydrophile in nature. Wires with dimples on its surface promote the detachment of gas bubbles from its surface by increasing hydrophobicity and reducing the bubble surface contact area. The addition energy between solid and liquid surface increases by increasing the hydrophobicity of the solid surface, that is the wire. A wire made of CNTs, carbon nanotubes, with a series of microstructures is more bettable than a smooth wire, and smooth wire has its own limitations. When such a wire vibrates axially during machining, the momentum is more efficiently transferred from the tool to the electrolyte in its vicinity. Due to this momentum transfer to the electrolyte, the flow of electrolyte gets accelerated, and along with the electrolyte, the mass transport of electrolysis product, that is the reaction product or the sludge, also increases, and the deposition of sludge precipitates on tool surface becomes difficult, because if sludge gets deposited on the tool surface, then the process performance will decrease and you may not get the desired component, and this provides stability to the machining process. And under identical machining conditions, feed rate is observed to double in comparison with a smooth surface. That means if you have a textured wire, feed rate you can increase as much as double as compared to the smooth wire, and if you are increasing the feed rate, definitely material removal rate is going to increase. That means the performance of the process is enhancing. The use of ribbed wire with sequential grooves in wire ECMM is also proposed. I have already shown to you in the earlier figure. Rifts in the wire assist in squeezing and dragging the gas bubbles liberated at the cathode out of the machining zone, and hence electrolyte conductivity remains largely unaltered. An improvement of 22% in the machining efficiency is reported when you are using this type of the tool. Although machining efficiency and quality improve significantly by the use of textured wire, but fabrication of such wires is really difficult, not that easy. Micro texturing of a wire is done either by chemical etching or by laser machining. Tool design in wire electrochemical micromachining, we have seen some part of it already. Now you can see here schematic diagram showing helical tools over here. So wire itself, this helical tool can work as the wire for electrochemical micromachining. Then cutting edge tool, this is the cutting edge tool, and fluted tool used in wire, this is the fluted tool as you can see over here. So all of them are designed to enhance the circulation of the electrolyte within the container, if it is the tank type, or otherwise also when jet type, and enhance the performance of the process. Now you can see here that electrolyte velocity vectors are given over here. Some theoretical work has been done by Dr. Divyans Patel. Let us not go into many details. Here helical tool enhances the flushing of electrolyte and electrolysis products from the machining gap. So it is just to show that feature of the flushing of the electrolysis products. Simulation image showing electrolyte velocity vectors in case of rotating helical tool. Tool design in wire ECMM continues. Tool design makes wire ECMM a two-step process. Also, mounting such thin wires on the setup for processing is not very convenient. To overcome these problems, researchers have proposed the use of micro drill, cutting edge electrode and fluted metal tube in place of a flexible wire for improving flushing efficiency in the process. And I have already shown to you these micro drill, cutting edge electrode and fluted metal tube in the just earlier slide. Micro drill and cutting edge electrode in the earlier figure are easy to mount on a spindle and rotate at a high RPM. The rotation can be up to 50,000 RPM depending upon the size of the drill. But please note it, such kind of rotation is not taking place in case of micro wires. They may be good for macro wire, but such type of rotational speed you cannot get for micro wires. When a cutting edge tool is used, the average current density in the machining gap is reduced due to increase in inter-electrode gap in the zone facing the flat surface of the tool. This leads to the reduction in the side inter-electrode gap. In case of a fluted tube cathode, figure C in the earlier slide, electrolyte is ejected from the micro holes. Workpiece is vibrated in the direction of parallel to the axis of the tube to ensure uniform spread of electrolyte. This is very important, and the amplitude of vibration is kept more than the whole spacing of on the tube. Useful in machining of thick workpieces and also in preventing the electrolyte from flowing to the non-machining region, which results in stray corrosion. So such kind of the techniques have been used for enhancing the performance of the wire electrochemical micromachining, and that performance you are evaluating by MRR, tolerances, surface texture, surface roughness, etc. Process parameters and characteristics. You can see here process parameter, power supply, which includes pulse frequency, current, pulse type unipolar or bipolar, pulse amplitude, duty ratio, very important, and voltage, whether it is continuous DC or pulse DC, and voltage will be very important over there in either of the two cases. Workpiece thickness, composition of the workpiece material, electrical conductivity of the workpiece material, very important parameter, and chemical stability also very important. It should not react with the electrolyte in any case. And mechanical properties, motion resolution, wire traveling speed, feed rate, workpiece wire vibration amplitude, and wire tension. Then you have the electrolyte properties, flow rate, composition, pressure, type of flow, temperature, viscosity, conductivity. All these parameters greatly affect the performance of the wire ECMM process. Like temperature affects the properties of the electrolyte, and once properties of the electrolyte are changed, the process performance will change. So normally temperature controller are used in these processes. Same way is true for viscosity, electrical conductivity of the electrolyte, and so on. And then tool, wettability, tensile strength, surface texture, diameter, and here tool means the wire length, chemical stability, profile. So you can see there are so many process parameters which should be controlled properly for getting optimum performance from the process. Now, how to evaluate the performance of the process, I have already mentioned to you in terms of material removal rate, etc. Effect of some electrolytic factors. At higher electrolyte flow rate, dispersion of gas bubbles and electrolysis products become more efficient. A uniform current density in the frontal and side inter-electrode gaps is established, and higher value of feed rate can be used for machining purposes. As the charge carriers in the cell increase, the anodic dissolution rate gets accelerated. Anodic means workpiece dissolution rate gets accelerated. If the tool workpiece feed rate is not increased proportionately, then side inter-electrode gap decreases and the machining accuracy deteriorates, because if side inter-electrode gap increases means the more material has been removed from the side and you will not get accurate dimensions of the machined feature on the workpiece. As feed rate is increased, frontal inter-electrode gap decreases because the wire comes closer to the workpiece and the replenishment of fresh electrolytes in this gap becomes difficult because the gap decreases, so definitely it needs higher pressure to get the same flow rate, but you are keeping the pressure constant. High electrolyte pressure also assists in the dispersion of electrolysis product, that is reaction product, from the machining zone, and machining can be performed at a higher feed rate, that is FM as abbreviated here. At high electrolyte pressure and flow rate, the tension in the wire must be increased for stable machining, otherwise you will not get the stable machining and wire may break or short circuit may take place. Effect of power factors: higher applied potential leads to an increase in material removal rate. It may be linear material removal rate or volumetric material removal rate. In pulsed power supply, pulse on time plays a key role in determining feed rate. Reducing the pulse on time decreases material removal rate, volumetric. Consequently, the frontal inter-electrode gap also reduces. And if the feed rate is not reduced, the short circuit will occur, and this is not desirable at all. For shorter pulse duration, smaller hydrogen bubbles are generated and they readily escape from the inter-electrode gap, thereby increasing volumetric material removal rate. Ultra short voltage pulse of on time say 20 nanosecond and duration of 160 nanosecond at a potential of 25 volt is tested in wire ECMM. As applied potential increases, material removal rate also increases and wider curves are machined. This is simple because once you are increasing the applied potential, current will increase, and if current is increasing, then definitely material removal rate is going to increase. Side inter-electrode gap can be minimized by working at a potential at which it's only marginally more than the tool feed rate to avoid short circuit. So, linear material removal rate is given by following equation: MRRL, that is linear material removal rate, 1 upon T means time duration, 0 to T on, I upon E into F dt. So, if you integrate this with proper limits, then you will get linear material removal rate, where T duration is the pulse duration, T on, that is given over here, is the pulse on time, T duration is given here, and E is the gram equivalent weight of anode material, this is the E, and F I have already told you, F is the Faraday's constant, 96,500 coulombs is its value, and I is the machining current, that current is given over here. Higher machining rate, that is MRRL, can be sustained without short circuiting with larger pulse duration. So, you have to be careful and you should take all precaution to avoid the short circuiting. Effect of tool rotation and tool workpiece vibration. Tool rotation initiates stirring, agitating action of electrolyte. Electrolysis products are flushed out easily, hence a uniform current density is established in the machining zone. Relative motion between the tool, that is the wire, and workpiece along the direction of the axis of the wire also causes the electrolyte to flow in the inter-electrode gap due to viscosity. Effect of workpiece thickness. As workpiece thickness increases, frontal and side inter-electrode gap become larger. Electrolyte pressure along the workpiece thickness decreases due to the drag force, and its replenishment becomes difficult in the deeper machining regions. In other words, you will not get that much accuracy as you expect in the deep machining. It becomes inevitable to reduce the tool feed rate in order to avoid short circuiting. This is the precautionary measure you should take. Tool workpiece feed rate. Increasing tool workpiece feed rate improves machining accuracy in wire ECMM due to the reduction in tool workpiece interaction time. It also reduces material dissolution from the workpiece in front and side inter-electrode gap both. Machining accuracy can be increased by increasing the tool workpiece feed rate. Tool workpiece vibration. Tool workpiece vibration aids in uniform distribution of electrolysis product in the machining gap and improves volumetric material removal rate. This adversely affects the machining accuracy as the side inter-electrode gap also increases with an increase in vibration frequency and multiple and amplitude, but the uniformity of curve also improves. Effect of process parameters on machining quality. Power factor. For a small pulse duration, large pits are formed due to high material removal rate. As the pulse duration increases, such pits are removed and polished surface is obtained. For very high pulse duration, the surface roughness deteriorates because of frequent short circuits. Optimal values of pulse on time and pulse duration must be experimentally determined for achieving high surface quality. Tool workpiece feed rate. Surface roughness is significantly influenced by tool workpiece feed rate. When the feed rate is low, time available for polishing of the surface is ample and low surface roughness is observed. Low tool workpiece feed rate is preferred for achieving better surface quality, but then machining efficiency is usually compromised. Therefore, an optimum balance between the two must be maintained. Tool workpiece vibration. High amplitude of tool vibration assists in flushing electrolysis products out of the machining gap and renewing the electrolyte more efficiently. This decreases roughness of the machine surface. I will stop here. Thank you very much.